Kia ora koutou katoa, it's Mrs. Goodson here, and this video is about the structure and bonding of covalent network substances, sometimes called giant covalent network substances. And it's video 13 for Chemistry 2.4 Bonding and Structure. And let's get on and look at these covalent network structures. So there are only limited examples that we need to worry about for covalent network structures. The first one is polymers, which we are going to look at a lot more in organic chemistry, but that is plastics held together with, these are all held together with covalent bonds, okay? So then we've got diamond and graphite, and so that is just carbon atoms. Diamond and graphite are both just carbon atoms. So this is an example of diamond. So remember that carbon has 4 valence electrons. So it forms these tetrahedral structures and it just keeps bonding to more and more carbon atoms. And so you get this massive network of carbon atoms bonded together and in a tetrahedral shape, and that is diamond. Silicon also has 4 valence electrons and it forms silicon dioxide with oxygen atoms. So you've got this silicon here and bonded to oxygen atoms, and it forms this big network of silicon and oxygen called silica or silicon dioxide, which is sand. Okay, silica is also known as silica. Silicon carbide is pretty similar, with silicon and carbon atoms bonding together to form these tetrahedral structures, this sort of network. So this network could just go on for ages, heaps and heaps of atoms joined up together, and silicon itself as well. And then carbon can form these layers of carbon atoms all bonded together, and these layers form graphite. So we're going to compare these two different versions of carbon, graphite and diamond. So covalent networks, also known as giant covalent networks, are made up of atoms. The particle is atoms. They're held together with strong covalent bonds. So that's where the electrons are shared in the bond. They form a tetrahedral arrangement. So you can have this 3D network. Now just remember that diamond is a 3D network and the others are 3D networks, but graphite is actually a 2D. We say it's 2D because it's 2D is two-dimensional, as in 2 layers, 2D layers, all right, compared with diamond. So diamond is 3D and graphite is 2D. Like in ionic structures, bonding can go on infinitely between the atoms, but covalent bonds are the rule here. So we've got non-metal atoms, so we form covalent bonds between the atoms. So this is a picture of silicon dioxide, also known as silica or quartz or sand, forms this crystal structure. All the silicon and oxygen atoms held together with covalent bonds, very strong bonds. Just a picture of diamond. You wouldn't believe that diamond and graphite or charcoal are made up of the same atoms. So the structure is the difference here. So we say they're allotropes of carbon because the atoms themselves are the same. They're all carbon atoms. But the diamond forms this 3D structure with a tetrahedral arrangement, and graphite has these layers of carbon atoms. And so that gives it very different physical properties. Also, in 1985, 1986, it was published these different structures of carbon, where the carbon atoms actually form these buckyballs with pentagons and hexagons, but like a soccer ball shape, with 60 atoms. These can be found in soot. And then they started to form nanotubes, and a lot of research has been done on these new materials since 1985. Okay, so buckyballs or Buckminster Fullerene is named after the discoverer Richard Buckminster Fuller. So that's another type of covalent network. So silicon dioxide is sand or silica, and each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom just to 2 silicon atoms. So you get this network here. If you have a look at this picture over here, this 3D tetrahedral network where it just goes on infinitely in different directions, forming a very strong network of covalent bonds, so that they have a very high melting point and a very high boiling point. It does not conduct electricity because all the electrons are held in covalent bonds, so there's no mobile charged particles, and it is insoluble in water and insoluble in nonpolar solvents. And if you click on that link, you'll get another video about silicon dioxide, or silica, as well. So silicon has a giant covalent structure. Each silicon atom shares each of its 4 outer valence electrons with another silicon atom. So silicon is a very, very useful metal, or metalloid, I should say, and it's got this network structure as well. So this video has been about describing covalent network substances made from non-metal atoms held together by covalent bonds extending in 3 dimensions, describing the structure and bonding of the allotropes of carbon, that's diamond and graphite, silicon dioxide and silicon carbide.